let's continue talking about the fundamental theorem of calculus. By the way, I already posted the homework assignment. Can you believe it? I usually forget to do it in a timely manner, but I did it this morning. Amazing. Fundamental theorem of calculus. I'm just reading in our textbook. They say the fundamental theorem of calculus is one of the greatest achievements of the human mind. Can you believe it? I don't know if I agree. Maybe I agree with that. The fundamental theorem of calculus is super important. If you recall, last time we had some kind of vague discussion about it, and we're going to talk in more detail about it this time. But the idea behind the fundamental theorem of calculus, at least remember there's like part 1 and part 2. Part 1 is kind of the weird one, but it involves if g of x is the integral from a to x of f of t dt, what is g prime of x? This would be the rate of change of this area, the area from a up to x. So what this represents, this is pretty weird, but you know, f of t is some kind of function like this. And if here is x, what it means is this is the area up to x. So that area right there is g of x. It's the area that you get when you measure the area up to x and you stop at x. And g prime of x measures how fast that area is changing if I were to change the x by a little bit. So the pictures I was drawing last time was something like this. If I change x to some, x plus h or something, then how much would that area change? It would change that much, the blue amount. So g prime of x measures this area, the blue area, this little strip there, all right? How fast will the big area change if I just push the x over by a little bit? All right. And what I said last time, which I hope you agree, I said this pretty informally, but this is x, and the y value here would be f of x. And what I said last time is the size of this blue strip depends entirely on how high up this point is, f of x, right? If this point was way down here, the size of the blue strip would be quite small. Whereas if this point was way up here, the blue strip would be much bigger. So the idea is that this g prime of x, which measures the size of the blue strip, it depends very fundamentally on f of x, just the y value, how high up that thing is, all right? And in fact, the fundamental theorem, I'm going to write it as a theorem this time. This is what I said at the very end last time. This is fundamental theorem of calculus, number 1. It says, well, you need to say if f is continuous, then here's the thing. The derivative of that thing which I call g of x, this weird integral from a to x, f of t dt, that what I just wrote is g prime of x, the derivative of that integral, equals f of x. This is the fundamental theorem of calculus. What I said just a moment ago, this blue thing, it depends very strongly on what f of x is. In fact, that was an understatement. Not only it depends on f of x, it actually equals f of x. That's what the fundamental theorem of calculus says. The derivative of the integral from a up to x just straight up equals f of x. All right? I hope that you have some kind of idea why something like this should be true. I want to go through the details. This is not going to take long, but to demonstrate why exactly, I want to convince you all that the answer truly is just f of x, not like something related to f of x, but it really straight up equals f of x on the nose, as it were. All right, so I'll call this a proof. It's like I said, this is not going to be terribly belabored. So just like I did before, I'm going to call this integral part g. So let g of x be that integral there, the integral a to x, f of t dt. And then we want to show that g prime of x, the derivative is f of x, right? Because that's what this says right here. The derivative of the integral thing is f of x. So we have to show that g prime of x. Now, when you have a weird function, like I'm talking about a derivative, I would like to just take the derivative. Now, when you take the derivative, you usually rely on sort of memorized tricks for finding the derivatives of various ordinary-looking functions. This is not an ordinary-looking function at all. That means the only option we have is to use the definition of the derivative, unfortunately. This is a nice little review. I hope you remember this formula. You may have to use this formula on the test, the definition of the derivative. Remember this thing? Lim h goes to 0, g of x plus h minus g of x over h. Usually we do this with a f, but I'm talking about g at this point. And this just is going to be more convenient if we factor that h out the bottom. Sometimes we do that. 1 over h and then times g of x plus h minus g of x. All right. And that g of x plus h minus g of x, actually you can see that very clearly on those pictures that I was drawing. Oops. In fact, it is the blue area that I've been drawing all along. See, if you have, let's say x is here, and then I have x plus h here. G of x plus h, this first part, g of x plus h means the area when you measure all the way up to x plus h. So that's this area. This is g of x plus h. Isn't that cute? The area all the way up to x plus h is g of x plus h. And then I'm subtracting from that g of x plus h, subtracting g of x. What is that? Well, that's the area only going up to x. So I'm trying to draw the same picture here. So that's this one, g of x, right? That's this area. And what do you get when you subtract? Sorry, I'm off the bottom. My screen is slightly bigger than these ones. So what do you get when you subtract the two areas? You get the leftover piece. So g of x plus h minus g of x is the sort of the leftover bit. It is the same thing as that blue rectangle I've been drawing all along. It's, come on. It's this much, right? That part is what you get when you subtract the two areas. So this is, can I just say, is the skinny rectangle, the blue one. The thing is, you can also write this like I forgot. I was about to say something which is not false, but I decided to say it a different way. That is the skinny rectangle. All right. So what we have here is just picking up where we left off up here. G prime of x is that stuff, right? But the thing in the parentheses, that's the area of the blue rectangle, right? So I'm gonna say G prime of x. It is lim h goes to 0, 1 over h, and then in here, it's the area of the blue rectangle, right? And you have to imagine, in this case, what is that area? The area of the blue rectangle, of course, is the base times the height. Now, I said rectangle. It's technically not a rectangle because it follows along the curve here, all right? But when you take the limit as h goes to 0, it basically looks like a rectangle whose height is f of x, right? You could use, its height, you could say is the left endpoint or the right endpoint, but when you're taking the limit as h goes to 0, it doesn't really matter anymore. So this, when I do this limit, is going to be, I'm just going to do the base times the height. The base here is h, b, it's h, right? That's this width. And the height is basically f of x, if I use the left side. If I use the right side, it'd be f of x plus h, but those are going to be the same anyway when h is going to 0. Anyway. And now do you believe me? You just get f of x, right? That's the point of this. This is the end. Shun. It's just because that difference is the blue rectangle that I've been drawing in all those pictures all along. And the area of that blue rectangle is f of x times h. But in the definition of the derivative, you divide the h out, so all you're left with is f of x. All right? It works out real nice-like. Okay, so that is the fundamental theorem of calculus, part 1. I'm going to write it again. This definitely you should memorize, although, like I said, this is not as useful. We're not going to use this as often as the other part, but this is the part 1 of the fundamental theorem of calculus. All right. It tells you, like on the surface of this seems very strange and not terribly applicable from day to day, even in a calculus class. It tells you how to take the derivative of an integral, which is, I mean, that's something, I guess, although I don't know if that's anything you ever wanted to know about. It tells you how to take the derivative of an integral, which has its variable in the top integration boundary. Anyway, let's just do some typical, homework problems about this are typically going to be quite easy. This is the kind of problem which looks far more complicated than it ends up being. So, for instance, if g of x is the integral from 2 to x, t squared plus 5t dt, then find g prime of 3. All right? So to find g prime of 3, first, I mean, not even looking at that weird formula there, to find g prime of 3, first you should find g prime of x and then plug in 3, right? This is how you find the derivative at a certain point. So first I'm going to find g prime of x. But this, you just use directly the fundamental theorem. The g is in here, and it says when you take the derivative of that, what you get is the inside function, but with x plugged into it. And so what I'm going to get here is g prime of x equals, because x is up top, I can use the fundamental theorem of calculus, and you just put x on the function on the inside. It's x squared plus 5x. This is weird, but this is what the fundamental theorem of calculus, the first version, says. When you have an integral with the x in the upper integration boundary, the derivative ends up equaling the function that's inside of the integral. I don't know if anybody wondered, what about the 2? What does the 2 have to do with anything? The answer is, the 2 has nothing to do with anything. It turns out the answer you get is totally independent of the lower number there. So if this, in this problem, instead of a 2, if it was like 10, the answer would be exactly the same. Strange but true. We're going to actually talk about that point in a moment. Anyway, this is g prime of x. I said find g prime of 3, so this is easy now. You just plug in 3. 3 squared plus 5 times 3, whatever that is. 9 plus 15, 24. All right. I hope you agree. This is very, very complicated looking on the surface, but when it comes to actually working out, like do the math, there's almost nothing to do. You just use the function that you see on the inside of the integral. Sometimes these can be a little trickier. Here's a harder one. It says, same sort of setup here, only it's like that. And I would like to find g prime of 4. All right. This is a harder one. What makes it harder is this, x squared rather than x. All right? The fundamental theorem of calculus tells you what to do if it was just x up there. What if it's some other function? How do you handle that? Well, this is the same that's true for every derivative formula that we ever learned. You know, when I told you, for instance, the derivative of sine of x is cosine of x, this only works when it's just literally x in there. If it was something else like x squared, you can't directly, I mean, you still use this, but that's not the whole answer, right? If it's something else in there, something more complicated, you have to use the chain rule. So that's actually what's going to happen here. Our base formula for this looks like this, but it has just x. But instead, what we're looking at has an x squared. So here, we need to use the chain rule. You know, when you're doing the chain rule, you always have like the function on the inside and then the function on the outside. In this case, the inside function is that x squared up there, because that's the thing which, like in our formula, it's just x. But here, it's a more complicated thing stuck inside instead of x. So we use the chain rule where like the sort of inside part is x squared, and the outside is the whole rest of the integral. All right? And so what we get when you do the chain rule, remember, what it is you take the derivative of the outer part with the inside still plugged into it, and then times the derivative of the inside. So in this case, we'll get g prime of x. I'm going to write out like in words what I just said. Derivative of the outside with the inside plugged into it. This is a weird application of the chain rule. And then times the derivative of the inside part. Now in this case, the derivative of the inside is easy. The inside function is x squared, so its derivative is just 2x. So that's what I'm going to put on the end there. And then what is the derivative of the outside part with the inside plugged into it? The outside part here is this whole integral. And the derivative of that whole integral, by the fundamental theorem, is just this function on the inside. So I'm going to write that function, 5t to the 4, but with the inside plugged in, the inside meaning x squared. So this looks like 5x squared to the 4. This is pretty strange in my opinion. And it will sort of test the limits of, do you really understand what the chain rule is all about? The insides and the outsides are confusing in an example like this. I use the function right in there. That's because the fundamental theorem of calculus tells me that the derivative of the whole integral is just this function in here. But because I'm doing the chain rule, I need to keep that inside part plugged into it. And so I plug, instead of t, I plug x squared. And this, if you want, you can simplify, I guess. 5 times x to the 8 times 2x. This is 10x to the 9. All right. That happens to be the derivative of x to the 10, although I think that's a coincidence. Any thoughts about that one? These are weird. Not, I wouldn't say hard really, but you really got to think very carefully when you do it so that you don't mess it up. Although it won't take you very long to do it in any case. Oh, did I answer the real question? I didn't. My real question was find g prime of 4, so we might as well do that. This is not hard. So g prime of 4 is 10 times 4 to the power 9. Right? Might as well actually answer the question. All right. This is about all I want to say about fundamental theorem of calculus, part 1. Like I said, part 1 is kind of an obscurity. It's not something that we're going to use very often. Part 2 we'll use all the time, constantly. Maybe like every day for the rest of the course, we will use fundamental theorem of calculus part 2. I guess that's not saying much, is it? Only 2 days left. So anyway, let's get to fundamental theorem of calculus number 2. I'm going to say this is the better one. In a sense, they both are expressing the same idea, although on the surface they look quite different, and this one is much more obviously useful. This is about what if I do you could say part 1 is about doing the derivative of an integral. This one is about doing the integral of a derivative. So it's like this. Do the integral of a derivative of something. So the thing on the inside is already the derivative of something. All right. Can we say anything about that? The answer is yes, you can. And actually, we don't have to go through a lengthy discussion of this, because actually there's sort of a trick where you can use the fundamental theorem part 1 to figure this out without going through back to first principles. So what I'm going to do is as we do, I'm going to call the integral from a up to x of f prime of t dt. I'm going to call that g of x. This is just like what we were talking about before, although only this time I'm considering when the thing on the inside of the integral is the derivative of something else. Anyway, so I'm going to say that, and then we know by number one, by fundamental theorem of calculus number one, that g prime of x is f prime of x, right? The fundamental theorem of calculus says when you take the derivative of something that looks like this, all you get is just whatever function is on the inside, all right? So in this case, g prime of x is equal to f prime of x. That means what we're talking about here, g and f, they are two different functions who have the same derivative. And what that means, they are not necessarily the same function, but they are different only by a constant. This is something that we talked about quite some time ago, actually. If two different functions have the same derivative, it means that they are the same, almost the same, except for perhaps they are different by a constant. So g and f have the same derivative, so they differ by a constant. So let's say you could write it like g of x is equal to f of x. No, I don't like that. All right. Plus a constant, right? Because g and f have the same derivative, that means they are basically the same function, but they might be different by a constant. All right? So this is g of x. It is the same as f of x. And one other thing we can say, I would like to sort of figure out what the c is in this case. Actually, you can figure out the c. We can determine the c. And the way to do that, you always need like one extra piece of information to find the c. This is like you did this on the homework for this week. You can do that in this case by looking at the specific value g of a. You know, usually finding the c involves checking one specific value and plugging it in. In this case, we can determine the c by looking at g of a. Sorry, I wanted these to be on the screen at the same time. I'll just copy this buddy, duplicate, put it over there. Is that confusing? It's like right next to it. I'll put it up here, right across the page break. All right, g of a. What is g of a? Well, g of x is like that, so this will say, I'm just going to plug in for x over there. Integral a to a, f prime of t dt. Integral a to a, that means the area under the curve measured from starting at point A and going all the way up to the point A. How much area is that? The answer is no area. There, between like A and A, there's no, that's not an interval. There's no area there. This is 0. All right? So what that means is when I go up here, plug in, I can plug x equal A and set it all equal to 0, right? Because it says g of a equals 0. So when I plug x equal a, it says 0 equals f of a plus c. So that means c is negative f of a. All right. We're just about done here. I hope you're not tuned out. We're about to get to the good part. All right, anyway, I'm going to rewrite this thing here. G of x equals f of x plus c, but I just said c is negative f of a. So g of x is f of x minus f of a. And now, just for fun, we're going to plug in x equals b. And this will be the fundamental theorem of calculus part B. Or part 2, g of b equals f of b minus f of a. And just writing, remember again the definition of g, which is just at the top there. It's the integral, blah, 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 blah. So what this says, g of b means the integral a to b, f prime of t dt equals f of b minus f of a. This is the fundamental theorem of calculus, the second part. It says the integral of a derivative is equal to the original function with the b plugged in, and then you subtract, and then you plug in the a. All right? There's actually, we're not typically going to write it in this way. Here I have in here the derivative of this thing, right? But you could also write it as this is some function, and over here is the antiderivative, right? All you need is that the derivative of this one is that, right? So rather than writing it like a derivative on the inside and the original function here, I'm going to write it like some original function over here and the antiderivative over here. So this, I'm going to write this as a theorem. We don't need to, the proof is what I just said. It says, so I'm going to write it using antiderivatives. If some big F is the antiderivative of the little f, then integral a to b f of x, the little f, dx, equals the big F of b minus the big F of a. This is the fundamental theorem of calculus part 2, which is, like I said, the more useful one. We're going to do this one all the time. I've seen tattoos of this one. Not in person, but I've seen pictures online of the tattoos of this one. I like to check out the math tattoos from time to time, see what the young people are doing these days. Getting tatted, people say that? Getting inked. Yeah. I'm not really up on the tat culture, if you can believe that. It's true. One thing I don't like is when people post like pictures of their tats, which is fine, but they most of the pictures that you see are like right after they got it done, and there's like blood on their arm, and it's all like all pink. I'm not into that. Just give it a few days, and then you can show me. All right, great. This is the fundamental theorem of calculus. What's so great about this? What's so great about it is just look at what this is. This thing over here, this is the definite integral, which before right now, you would have said is very, very hard to compute. This is the thing you have to do as the limit of the Riemann sums, right? Even for a simple function, this will take you 15 minutes to figure out what the definite integral is, right? And that's only if it's a very simple function, like because you have to use those formulas for the sums of the I squareds or whatever. If your function is like x to the 4, then you're going to need another special formula for the sum of I to the 4, right? The left side of this equation is very, very hard to do, whereas, I'm just going to say hard, very hard. This stuff over here, though, very easy. All you do is you plug in two numbers to the antiderivative and you subtract them, all right? Really, the subtracting, of course, is easy. The only somewhat hard thing is you have to know what the antiderivative is. So this over here is all about antiderivatives. And I'm going to say, this is easy, like, if you know how to do it. But, I mean, you do know how to, like you just did one on the quiz, right? I hope you did that one. Anyway, it won't take you 15 minutes to figure that out, right? It'll take you like 15 seconds, depending on how hard the formula is. The right side is much, much easier. The left-hand side there is kind of like, in most cases, totally impossible. But the right-hand side is, in most cases, much more possible, right? That's what's so awesome about the fundamental theorem of calculus. I suppose without using the fundamental theorem of calculus, you could try to do the left side by estimating using the rectangles or whatever. That really is only convenient if you're using a computer to do it. Like if you really wanted to solve real world problems, you basically need a computer to evaluate the left-hand side in the real world. Whereas if you know the fundamental theorem, it becomes easy to do this stuff by hand. Really super awesome. And I think the human technology would not exist in the way it does if not for the fundamental theorem of calculus. If people didn't know how to do integrals by hand, you could do it by a computer, but I don't think people would have figured out how to build a computer without being able to do integrals, right? Like, this is super important in the development of the human race. Anyway, let's just try and do some examples here. I got some to try. I got some for you to try. How about my favorite example? Integral 0 to 1 of x squared dx. Remember, this is the area under the parabola from 0 to 1. And I told you, just because I told you, this area here is 1/3. And actually, with great effort, we were able to compute that area as 1/3 doing the Riemann sums thing. But here you'll see how much easier it is to do it using antiderivatives. All right, what that is, just according to the fundamental theorem of calculus, it is big F of 1 minus big F of 0. You always do the top one minus the bottom one, where the big F, in this case, is the antiderivative of x squared. So you have to know what the antiderivative of x squared is. So in this case, big F of x is the antiderivative, which is 1/3 x cubed plus c. All right? And now I can just plug that in. So this stuff here becomes I'm plugging it in. 1/3 times 1 cubed plus c minus, and parentheses, 1/3 times 0 cubed plus c. Right? And then we can simplify, and we're going to get 1/3, aren't we? This is 1/3 plus c. Distribute the minus sign. Minus, that's going to be 0, right? 1/3 times 0 cubed is 0. And then minus c. The c's will cancel, and we just end up with 1/3. And that's it. All right. I hope you're convinced. This is much, much easier than doing the Riemann sums. You should expect on the final exam, I'm going to ask you to do a bunch of integrals. You better do it this way, unless I say use the Riemann sums, and then you will shake your fists at me. But this is basically always easier. All right. Great. Let's talk about a little notation here. So the way that I just wrote it is a little inconvenient, just because you kind of do this thing, and then there's like a little side work over here, which I didn't even have room on the side. I put it right there, but then I have to make this big old arrow here. There's a special notation for indicating this as like a single intermediate step. So we're going to write this, a special way to write it, like this. So what I'm about to write is meant to express the same thing, only without sort of splitting it out to a little sidebar, which then comes back. I am going to just right away do the antiderivative here, 1/3 x cubed. I'm not going to write the plus c. That's because it turns out that the c, if you do this right, the c's will always cancel in the end anyway, because you're subtracting the big F of b minus the big F of a. Each of them has a plus c in it, and when you subtract, the c's cancel. So I'm not going to write the plus c. We do need to remember what the values are, and here's the special way of writing it. You put that little bracket there, and the 0 and the 1. So what the bracket means, well, I'm just going to write a little commentary here. You do the antiderivative, which I did. Antiderivative. No plus c. Although if you do put the plus c, it's going to cancel out anyway, so you might as well not put it. You do the antiderivative, no plus c. And then this thing, this bracket here, 1, 0, this means we'll plug in and subtract. So that bracket there is kind of like an operation, which means in the next step, I'm going to plug in the 1 first, and then subtract, and then plug in the 0. So I just continue immediately. 1/3 times 1 cubed minus 1/3 times 0 cubed. And this, of course, is 1/3. That's the same answer. So this is the way that I would write one of those. Right? Very, very simple when you write it using this little bracket there. All right? I'm going to try one more and then see what you guys think. So let's try integral from 2 to 4 of 3x minus 2 dx. What's it going to be? I'm going to write it the way that I wrote that one up there. So the first and kind of only step, there's not many steps here, do the antiderivative. I get 3 times 1/2 x squared minus 2x, right? That's the antiderivative. And then I'm going to do the bracket here with the 4 and the 2. That means I'm about to plug in 4. and subtract and plug in 2. So let's do it. 3 times 1/2 times 4 squared minus 2 times 4. There I plugged in 4. Make sure you plug it in everywhere. Everywhere you see x, you replace it with a 4. And then you subtract. You go through the whole thing again. Plug in 2 everywhere. 3 times 1/2 times 2 squared minus 2 times 2. There you go. That's it. This, by the way, I don't know if you remember. This was the same function that I asked you on Wednesday to do using the Riemann sums, and it took you like 20 minutes. There. It's a lot easier this way. That's how awesome the fundamental theorem of calculus is. All right? Any questions about that? All right. I got some for you all to try. Yes. Just several random antiderivatives to do. I mean, definite integrals to do. 2x squared plus 1 over x to the 4. You know, some of these you might have to transform them like you did on the quiz. You have to multiply it out first and then do the antiderivatives. You might have to do that for some of these. Next one, integral from -1 to 1 of 2x plus 3, the whole thing squared. And then I got integral 5 to 10 of x squared plus 7 root x over x to the 5. And finally, integral 0 to pi of sine x dx. That last one is kind of interesting, what it represents as an area. You know, these all represent areas. Sine of x, of course, looks like that. What this last one here represents that area right there. I don't know if you ever wonder. What's the area under that first bump of sine of x? Well, you'll find out. You can make that one happen. Okay. Yes, certainly. All right. Okay. Feeling good? Let's take a couple more minutes and then we'll go over. I have one more thing to say before we leave. Actually, maybe we should start doing them right now. I'm going to run out of time. It looks like people are doing pretty well. I'm going to try and go through these real quick. So the first one, you want to rewrite, first of all, using a negative exponent, like so. It may help to keep things straight to be a little careful. You don't have to be too careful, but at least be cognizant of the integral sign. Like here, I wrote the integral sign again and the dx again. It's because this step was not doing the antiderivative. I just rewrote, I was just rewriting this to be x to the minus 4. In the next step is when I actually do the antiderivative. I get 2 times 1/3 x cubed plus 1 over minus 3 x to the minus 3. And then I put the bracket 1 and 3. All right. In that step, I did the antiderivative. That means I should not write the integral sign anymore, and I should not write the dx anymore, and I should write the bracket, right? And then you plug those numbers in. So you get 2 times 1/3 times 3 to the 3 plus 1 over minus 3 times 3 to the minus 3. Minus, go through again, plug in 1. 2 times 1/3 times 1 to the 3 plus 1 over minus 3 times 1 to the minus 3. Typically, I would expect you to just leave your answer like that on our test or something, all right? Unless I would tell you specifically if I wanted you to simplify. Although something like that, I wouldn't ask you to simplify. Any questions about that one? Great. The second one there, you've got to, again, rewrite this. You may be tempted to just do the thing with the power here. Increase this 2 to a 3 and divide by 3 in the front. Actually, that is not going to give you the correct answer. It's because this stuff on the inside screws it up. So instead, you have to actually expand the stuff on the inside like this. This, when I do the FOIL, I get 4x squared on the front. On the middle term, I get 6x, and I get another 6x on the outside, so that adds up to 12x. And then plus 9 on the end. I'm going to move these guys down. All of this. And so, doing the antiderivative now, 4 times 1/3 x to the cubed plus 12 times 1/2 x squared plus 9x. And I evaluate at 1 and minus 1. I hope this is what you all got. And then you just subtract them. 4 times, maybe I'll write 4/3 times 1 cubed plus 6 times 1 squared, which is 1, of course, plus 9 times 1. Subtract, and then 4/3 times minus 1 cubed. They're so easy, it's kind of boring to write them. Right? I hope you got that or something like it. Okay, the next one was another one where you need to rewrite and sort of distribute things, although it's a little different. I think there were ones on the homework this week kind of like this, although they were just plain antiderivatives, not definite integral. But this one I would, before doing the antiderivatives, you write this as x to the minus 5 and then distribute it. Or you could think of just directly canceling powers of x. Well, you should end up with x to the minus 3 plus 7x to the negative 4.5, right? The one up top, root x is x to the 1/2, and then you subtract 5 from the exponent. And then these guys, you do the antiderivatives. So it's 1 over minus 2x to the minus 2 plus 7 times 1 over negative 3.5 x to the minus 3.5, right? And then I plug in 5 and 10 equals whatever. Can I just say? You get whatever you get when you plug in 5 and then subtract and you plug in 10. I hope folks got that one. And then let's just talk about the last one. The last one I think is kind of cute, like I said, because it represents the area of one of those lumps in the sine function. What is it? You get, immediately do the antiderivative. What's the antiderivative of sine? It is? Somebody shout it out. You remember it. Negative cosine, yeah. The derivative of sine is cosine. The antiderivative of sine is negative cosine. And then I'm going to plug in 0 and pi. So this is minus cosine of pi minus negative cosine of 0. Cosine of 0 is 1, and cosine of pi is minus 1, right? The graph of cosine looks like this, where this is pi. This is 0, of course. So that's 1. That's minus 1. So this is minus cosine of pi is negative 1, minus 1. And that all adds up to 2. Can you believe it? 2 is that area. This is very strange in my opinion. Another one of those cases where, I don't know, whoever invented sine and cosine, minding their own business, creating trigonometry. I don't think they intended to make the area of one of these lumps equal 2, but just by some kind of magic, it is that area is 2. Strange but true fact. All right, weird but true. My kids love those books. They got weird but true books. I never seen this fact mentioned in a book for children. All right. I said I had one more thing to talk about. We got 10 more minutes, and that should be plenty. I hope that those worked out for you. I would like to just real quickly talk about some basic properties of the definite integral. I actually don't have a lot to say about these properties, but one of them you need to use on the homework, which is why I wanted to make sure I get through the list here. Properties of the definite integral. Because we know now that the definite integral is computed according to antiderivatives, it's basically the same as an antiderivative, only you have to plug in the number and subtract the other number, right? But as far as like a mathematical operation, the interesting part of the definite integral is done by doing an antiderivative. So here are some very simple properties of the definite integral. If I have the integral from a to b of two things added together, actually you already did this in all the examples that I just showed you. If you have two things added together, you basically consider them separately. You do the antiderivative of the one thing, and then you do the other thing, and then you add it all up at the end, right? So this, what that means is this. The antiderivative of a bunch of stuff added together on the inside is the same as just adding together the two antiderivatives. All right? When you are adding things on the inside, you don't have to do any special rules like for the derivative, if it's multiplication, you have to do the product rule or whatever. In an antiderivative, if it's addition, you don't have to do anything. You just do each part separately. All right? Same with a minus. I don't think we need to write that also. There's another rule which also you have been doing, although you probably weren't thinking about this. If you have a constant times your function, this is the same as just pulling the constant out of the integral. All right? I said you were actually doing this all the time. I don't know, the way that I write them, it's a little more clear. Like when I did the integral from a to b of, say, 3x, I made this 3 times 1/2 x squared, and then a to b, right? And nobody said, why did you just leave the 3 like it is? I mean, that's just how the antiderivative works. It's the same as this. If you have a constant multiplied in front of your function, what happens to that constant? It just stays the same in the answer, which is exactly what you see happening right here. All right, so that's the second important property of the integral. I will say these are super important, but they're not really the kind of thing that I'm going to tell you to memorize, because they're so important that you've already been doing it without even knowing about it. So these ones you use all the time. It's like breathing. You don't really have to. You don't really have to think about them. You will just naturally do them correctly. All right, here is one more. Actually, this one that I'm about to write is the one that you will see on the homework. Sorry, no C in there. Just the integral from a to b is equal to minus the integral b to a f of x dx. This is weird and doesn't actually make a lot of sense when you think of this in terms of areas. It says if I take the area going from A up to B, this is the opposite of the area if I go from B up to A, even though typically the B is greater than the A. So you should think of this one as kind of backwards. So like as an area, actually this doesn't really represent an area in the ordinary sense, but you can still, it's actually kind of obvious why this is true, because this one equals big F of B minus big F of A, whereas this one would equal, just this part of it, would equal big F of A minus big F of B. And these are opposites of each other, right? Which is why that formula is true. You can swap the two numbers in the integral sign, and the effect of that is to introduce a negative sign. Strange but true, all right? We've got a few minutes. I have 3 more properties here. I might as well tell them, and then we can go get out of here. Here's another one. This was very closely related to the previous one. What about integral from A to A? That is, you could think of this in terms of areas, like the area from A up to itself. We already talked about this once earlier today. This is 0. This is an area across no interval at all, right? You go from one point, but you don't go to another point. You go to the same point again. That makes no area under the curve. So this integral is 0. It's actually, this is obvious if you think of it in terms of the fundamental theorem. What this equals is big F of A minus big F of A, and that's 0, right? So it's pretty clear. The integral from A to A is always 0. All right? One more? No, two more, I said. Okay, this one is a little strange, maybe. Integral from A to B of f of x dx plus the integral from B to C of f of x dx. This one makes the most sense if you think of it in terms of areas. It says the area from A up to B, and then also I add the area from B up to C. All right? Any ideas? Can you envision this in your mind? You take the area under the curve from A up to B, and then add onto it the area from B up to C. Can anyone say what should that add up to? Yeah? Yeah, it's the area from A all the way up to C, right? This is like, the left side is kind of breaking that big area into two chunks, but they should add up to the same big area. So this is the integral from A to C, f of x dx. Great. That one we're not really going to use very often, but every so often it comes up. And then finally, it's kind of a complicated one to write, but it's obvious that it should be true. If I have two functions and one is bigger than the other, f of x greater than g of x, then the area under f of x is bigger than the area under g of x. So if f of x is bigger than g of x, that means when you look at the graph, the f is actually above the g at all times. Then it means the area under the f is bigger than the area under the g. So if f of x greater than g of x, really it's only necessary that the f is above the g throughout the whole interval, then integral a to b f of x dx is greater or equal to integral a to b g of x dx. Right? If the f is above the g, then the area made by the f is bigger than the area made by the g. All right, and that's my random list of formulas. Sorry to give you the random list without really saying much more about them. Time to go.